Myrta Grüning from Belfast, and she's going to talk about nonlinear optics from real-time dynamics.
Okay, thank you for the introduction, and thank you for giving this opportunity of presenting this work, which is a long and close collaboration with Claudio Attacalite in Marseille. So when we started this work was about 10 years ago, and there were nice tools available for calculating optical absorption. So here I'm showing the optical absorption calculated either with the independent particle or with the GW plus beta salpeter approach for a monolayer sheet of hexagonal boron nitride. And here one can see the importance of going beyond the independent particle to get excitonic effect. However, there were no existing tools for going beyond the linear response and going to nonlinear optical properties. So in fact, there were a few works. For example, this is a calculation using a beta salpeter-like approach for the second harmonic generation of gallium arsenide, but they were just, I would say, sparse, and there were not tools available to the community. On the other hand, if we just go to the other method to calculate optical properties, we have both linear response for time-dependent density functional theory, but also implementations and code available for real-time approach. And when use real-time approach has the advantage that can treat on the same footing linear and nonlinear optical properties, and even aspire to go beyond and go to extreme nonlinear and time-resolved spectroscopy. So the problem with time-dependent density functional theory is that when we use standard approximation, we miss this long-range electron-hole correlation that I've shown for this example on monolayer hexagonal boron nitride is essential to capture excitonic effect. So our work was to just try to develop and implement a beta salpeter-like real-time approach. So we did this with Claudio Attacalite and Andrea Marini. And so I will just cartoonize our paper. So if you want to go into the details, you can just refer to this publication. We looked at what are the key ingredients of the GW plus beta salpeter. So everything is grounded in many-body perturbation theory, and then an important thing is that we just start from cone-sham and energies and block functions. So everything is first principle. Then, of course, we need to correct for the band gap problems in density functional theory. So we use the GW approximation. And then finally, for the response, we are using the Coulomb-Hall screen exchange approximation for the response kernel. So this is a quite good approximation. It gives very accurate result. And on the other hand, being a static approximation, it makes also the calculation not too heavy. So what we did was just to take the same ingredient, but found everything on the non-equilibrium Green's function, since we want to have a real-time approach that may go to time-resolved and even to extreme nonlinear phenomena. So we start from the Karnoff-Baim equation, and then we apply exactly the same assumption approximation. So we use cone-sham energies. So we are first principle. We correct them within the GW approximation. And then for the self-energies that are in the Kaim-Banov equation, we approximate the retarded one with a Coulomb-Hall screen exchange approximation, and then we just put to zero all the lesser and other self-energies. So with this approximation, we just reduce to a simple equation just for the lesser Green's function. So the lesser Green's function is linked both to polarization and current, so coherent motion, and also we can look at the population, so at excited state carrier dynamics. So in this equation we have the small h, which is the Hamiltonian of our Conchem system. So we calculate this from a DFT calculation. Then we can calculate the correction using GW. So U is the interaction with the field. So we are in dipole approximation. So it's just a time-dependent signal that we input. And then we have the change in the Hartree potential due to the change of the density, and then the change in the Coulomb-Bose-Green exchange self-energy due to the change of the lesser Green's function. So as I said, we have access both to polarization and to the excited state, excited carrier dynamics. In this talk, I will just focus on polarization. So regarding polarization, this is just a reminder that may be useless, that one cannot use the formula for finite system when calculating the polarization, relying only on the density. And this is just a cartoon to show that if we just trivially get this equation, we have problems, because if we integrate over all space, it will diverge since the density is not decaying. If we try to just restrict this to a unit cell, it's not well defined, because it depends on the choice of the density. So, of course, this is a problem that has been solved in the 90s, and we have here authors of the key papers. And so what we need to do is to redefine the position operator consistently with the periodic boundary conditions. And then, of course, this is a purely many-body object. Then if we manage to write our wave function as a Slater determinant, we can just get the expression that you have seen also in the previous talk for the position, and then to get the polarization, you just get multiply by the charge and divide by the volume. So this is for static polarization. For dynamic polarization, we rely on work of Ivo and Vanderbilt. So here in the paper, he just used the density matrix, but in the approximation we are in fact, the lesser Green's function and the density matrix are just related by a trivial coefficient. Instead, so we just write this as the product of this periodic part of the dynamic Bloch electrons, and then the polarization can be just written in this way, which is very similar to the static polarization. The difference is here that the sum is on the field states. So the problem here, you see that we have the polarization, which is only implicitly depending on the Green's function. So what we did here is just to rewrite our equation of motion. So the details are in this paper in terms of this periodic part of the Bloch electrons. Here you have exactly the same ingredients. Here, this is just the interaction, the dipole interaction between the system and the field, and it's not the normal dipole operator that you would expect. It's the covariant dipole operator, which is consistent with the definition for the polarization that I've shown you before. So if you want to see how this is calculated, it's basically with finite differences. You can look at the paper. So now we have a theory that will allow us to use many-body to just include many-body effects in nonlinear optics. And then the first question is that important? Because, of course, this will just imply a bit of more computational effort with respect to the independent particle. So just as an example, this is the second harmonic generation in single-layer monoshell cosenites. So second harmonic generation, we pump a given frequency, and then we just, in transmittance, we not only have the residual, the signal at the frequency, but we also have harmonics, and in particular here we are looking at the second harmonic. So there were a couple of experimental papers that pointed out, that measure the second harmonic intensity at some given frequency. And just to put this in context, as a comparison, I'm giving here the coefficient for the bulk, so for gallium selenide bulk. So you see that there is an order of magnitude with respect to what is measured in the bulk. And even if one look at molybdenum disulfide monolayer, which is known to have a very strong second harmonic intensity, this is also quite larger by, so this is 2 orders of magnitude, this is 1 order of magnitude. So it seems that these are very interesting materials for second harmonic generation. However, if one look at the existing theoretical calculations, those are showing values that actually are not that impressive, and they differ about 2 orders of magnitude. So since those are calculations done in dependent particle or time-dependent density functional theory, which also miss this electron-hole attraction, and they are done out of resonance, so are done in the static limit, one may wonder if the huge difference we observe here is due to excitonic effect. So this is our computational setup. So we are sending a monochromatic wave. So we are calculating, as I said, the cone-sham and GW correction using DFT and GW code. Then we integrate the Euler-Lagrange equation, and from that we calculate the polarization using the dynamic Berry-phase expression I showed you before. Then we need some post-processing. So basically we just sample a period of this polarization, and we use what is the Fourier matrix inversion. And this will give us just a point on this spectrum. And of course, we have then to just input different frequencies between a range of frequency we are interested in to obtain the whole spectrum. So what are the results? So this is done in the static limit to compare with existing results. So we don't have an exact comparison since they were using hybrid functionals. However, we see that we get the same order of magnitude. We also see that there is not really a difference between the independent particle and the GW plus beta salpeter. In fact, when we add both the local field effect and the G0, W0 corrections, we have a blue shift of the energy, which can correspond to a reduction of the intensity. And then when we just add this electron-hole attraction, we increase the intensity again, but still at the level of the independent particle. So then we calculate the spectra. Here in gray, there is the absolute intensity, and I also have the imaginary and real component of the second harmonic coefficient. And again here, so here I show where the measurement was taken, and you actually see that in independent particle we would get a larger value than what we would get with G0 plus the beta salpeter, just for this effect of adding the G0, W0 that diminished the coefficient, and then the beta salpeter just get a bit more at excitonic resonance. For example, here it's larger, but still it's everything at the same order of magnitude. And the same with indium selenide. We observe a general increase of the intensity, but it's really nothing close to order of magnitude that are observed in the experiment. So, well, there was a bit of panic. We were just hoping to get a striking excitonic effect for this material of 2 order of magnitude. And instead, we even don't get close to what are the experimental values. So instead of 2.4 nanometer per volt, we get 120 picometer per volt. And instead of 6.4, we get nanometer per volt, we get 430 picometer per volt. What we know actually, if we trust, and we trust actually in our method, is that we can exclude excitonic effect as the source of difference between what is observed theoretically and what is measured, or better, estimate. Because that's the problem with second harmonic generation. It's not a direct measure, but it relies on a model. So there was this quite nice paper which actually discussed the difference that was observed for three different measurements on the monolayer of molybdenum disulfide, in which the measured value of the value that was given in this experiment just ranged over 3 order of magnitude. And they see that, well, it depends on what you use. So some of this experiment use still a model, which is a bulk model, to extract the second harmonic generation coefficient, and instead some other are a bit more careful and use a model of a sheet on a substrate. And then they also give this formula in terms of the refractive index of the 2D material and of the substrate, and then one can compare methods that just use this different model and get some factor just to relate these two estimates from this experiment. And if we just use this formula for our material, we see that we have about a factor 30, and this factor 30, which can indeed account for the difference between what we are calculating and what is measured. So if we go back, it's about a factor 20 between what we calculated here and what is measured. So we believe that the problem is the fact that the experiment are using a bulk model rather than a sheet on a substrate. And in fact, after we submit this to the article to archive, Claudio received an email pointing out to a paper that was published while we were just doing our calculations on I think indium selenide, and this experimental work used a sheet on a substrate model, and indeed they get a value which is in good agreement with what we have calculated. So just not to give the impression that there is no importance at all of adding excitonic effect. So here are some more model for 2D system and second harmonic generation. This is molybdenum disulfide, and then we have this model, this systems that are still not synthesized, so silicon carbide, gallium nitride, and silicon oxide. And in this case, at excitonic resonance, we observe 2 to 4 times the intensity increase due to excitonic effect. We also looked at rather different systems. So these are 1D nanostructures, so either nanotubes or nanoribbons. And we looked in this case at the third harmonic generation. So here in magenta, we have what you will obtain in independent particle using the DFT energies. Then if you correct with the GW, you will obtain this green curve. So you see a strong reduction, and this is due to the sum rule. So if we blue shift, then the intensity comes down. And then if we add the electron-hole interaction, we will have a redshift again. But we also have, with respect to the original Kohn-Sham independent particle calculation, we have a strong redistribution of the intensity. We also looked at other properties like the intensity-dependent refractive index and 2-photon absorption. So this is just, if you look at the polarizability at the laser frequency, you can get, of course, the linear response. But then you will also have terms which depend cubically on the field. And you can get this by in an experiment if you just put a lens which just focus the beam. And then, of course, if you move slightly your sample, it will experience a very different field. And so you can just look at how the polarization is changing when you change the intensity. And we are doing quite the same in our computational setup. So it's very similar to what we have done before, but we are just looking at this for different field. And then by extrapolation, we are able to get the 2-photon absorption or Kerr effect spectra. And this one we apply to a system which you really need to describe exciton, as shown at the beginning, the hexagonal boron nitride. If you don't use the beta-salpeter, you really don't get any feature. And here, what we have done, we are just calculating the absorption, which is in green, and the 2-photon absorption, which is in blue, for the monolayer and for the bulk. So for the monolayer, it's not really interested, since the exciton are all degenerate. So the two spectroscopy really probes the same exciton, while if you go to the bulk, where you have dark exciton, which is lower than the exciton which is observed with optical absorption, you then, by 2-photon energy, you are able to detect this exciton, this otherwise dark, in conventional optical absorption. So up to now, I've shown you how to just go from beta-salpeter to a real-time beta-salpeter and include in that way accurately electron-hole attraction. However, one can also think of trying to include proper electron-hole attraction into a TDD, time-dependent density functional like approach. So I will go briefly through it. And what is interesting is that since we are in this real time, we are working at Q equal to 0, we cannot just play just using the density and looking at the optical limit, as you will do in linear response. But since we have an explicit macroscopic electric field, we have to look at the density and at polarization, at the macroscopic polarization, as well as the key quantities of our density. So that will be a density and polarization functional theory. And then when we are in the Kohn-Sham method, we don't not only have a microscopic effective potential, but also a macroscopic effective field. And that, of course, is the total field plus an exchange and correlation part. And this needs to be approximated, like the exchange and correlation potential. And since we didn't have any better idea, we just go to what are the approximations that are existing in linear response. So for linear response, there are several approximations for the optical limit of the kernel, which is this object here. And so here we have the change in the exchange correlation potential. It's just given by the kernel times the change in the density. And we just replicate the same for this exchange correlation field. It's just depending on the change in the polarization times a kernel. This is, of course, a tensor now, not just a simple function. So, of course, there are relations between the field and the potential and the polarization and the density. If we use this, we can just build a relation between the two kernels, so in the optical limit. And using this, we can then write, of course, in a linear response approximation, the exchange and correlation field in this way, where this alpha here are or can be derived from existing approximation for the exchange and correlation, density exchange and correlation kernel in the optical limit. So this is what we have done in this paper. So there I've just looked at several exchange and correlation approximation. Here I'm only reporting the simplest one, which is given by semi-empirical parameters, which are reported in this paper. So here, this is just optical absorption, so I'm just reproducing, in fact, the results from this paper, just to see that everything is fine. So here you see this will be the random phase approximation, and then if you include this is for silicon, this macroscopic exchange and correlation field, you manage to capture excitonic effect. Of course, we know this work only for semiconductors, but for semiconductor, it's quite an efficient method to get excitonic effect. And this is just a result for bulk semiconductor. So we have quite good agreement with experiment for the gallium arsenide if we just exclude this feature here at low energies. This is not true for the few points that we have for the cadmium telluride, but unfortunately we only have these few points and we cannot just explore higher frequency to see if RPA is better than our approach in this case. Okay, so here I'm concluding, so I'm just showing a way to fill in this quadrant to have method for which we can approach problems for which this it's important to take into account electron hole attraction and just explore then phenomena in the nonlinear regime. So I just went from the Bethe-Salpeter and just building a real-time approach, or going down from time-dependent density functional theory and try to put some approximation which can take into account this electron attraction. And so this code is available to everyone, so you can just get the latest version of Yambo where this is implemented. So thank you very much.
thank you very much for the very nice talk. Are there questions? Yes.
A simple question about this nonlinear response. Will this method apply for periodic system?
Yes.
Okay.
Yeah.
Non-limited to molecular.
No, actually, since we are, well, you can do for molecules, but then the polarization, you will just use the other formula, the formula for finite systems.
We know that nowadays there is issues regarding to the dielectric constant for the two-dimensional material.
Mm-hmm.
So because possibly Yambo code also took into account the slab vacuum model, right? Or
Sorry?
How the dielectric constant for the 2D materials was calculated during this calculation?
Okay.
Because it's a two-dimensional, it's not periodic boundary condition fully.
Yeah, so actually, yeah, thank you for the question. Also in experiment, what they report is the effective second harmonic. So we have an effective thickness. So we just calculate in a supercell, but then we just take away the supercell dimension and we use this effective. So if you look in the paper, all effective thickness are reported.
Okay.
Yeah, thank you for the question.
Thank you.
Thank you very much for a good talk. I have many questions here, so that but
just one
quick.
and then
okay.
then
Well,
lunch.
first question: why you need this dynamical Berry phase? You're directly calculating the current, right? So you can calculate the current. So why you need this formula?
Well, yes. So the current will have the problem that was mentioned by Massimiliano, because then there will be. I mean, I'm just have no local somewhere. Yeah, I have a no local operator, so I would have to include in the current the contribution from this no local operator, and this is not also trivial. So I don't have. So current has also their problem. It's possible. We are now trying to implement both also to see. So just going on instead of using a length, we're using a velocity. But I mean, there are problems there as well. There are problems as well on numerical problems. But the biggest problems will be that you would need to just give the contribution that comes from the non-local part. And in this case, you don't have this problem.
Usually, when you do an experiment on second harmonic generation, you have critical phase matching conditions. So the intensity of the emitted phonon depends crucially on the orientation of the crystal. Have you considered many orientation? Or?
Yeah, I mean, those are just taken for some particular orientation. But yeah, no, I don't have. Sorry, I don't have anything to simulate the phase matching condition, and so there may be discrepancy. In fact, when the experimentalists say a good agreement was a factor 2, but I mean, we were quite happy. I mean, I can accept some factor 2, but the problem of 2 order of magnitude was more worrying. But yeah, no, we only calculate what comes out. We don't have anything to just look at the propagation and phase matching condition.
Okay, so I see no more questions. So let's thank our speakers again. And so that's then the end of the session. Now there's lunchtime, and then we reconvene at 3 here. So.
Just an announcement for the members of the Scientific Advisory Board that please let's meet outside. We're going to have our